What is the Chinchilla Scaling Law? In 2022, researchers at DeepMind, led by Jordan Hoffman, published a paper titled Training Compute Optimal Large Language Models. They trained a model named Chinchilla to test a hypothesis. Are we building models that are too big for the amount of data we are giving them? The Chinchilla Scaling Law states that for every doubling of the compute budget, the number of parameters and the number of training tokens should be increased in equal proportions. To get the best performing model for your money, you should have roughly 20 tokens of data for every one parameter in the model. So one might ask, why does this matter? Before Chinchilla, models like GPT-3, which was around 175 billion parameters, were being trained on relatively small amounts of data, about 300 billion tokens. According to the Chinchilla findings, GPT-3 was undertrained. It was a massive brain that had not read enough books. DeepMind built Chinchilla with only 70 billion parameters, which is much smaller than GPT-3, but they trained it on 1.4 trillion tokens, which is much more data. Even though Chinchilla was 2.5 times smaller than GPT-3, it significantly outperformed GPT-3 on almost every task. The researchers found a mathematical relationship between the optimal model size n and the amount of training data d for a given compute budget c. If you have a fixed amount of computing power, you reach the sweet spot of performance when, number 1, the model size n is scaled appropriately, and number 2, the training data d is scaled by the same factor. If you make the model larger without increasing the data, you get diminishing returns. You are spending money on a bigger brain that does not have enough information to fill it. In the world of AI, there are two main ways to build a massive model. Imagine you are building a giant library. The first approach is dense transformers. This is like a library where every single librarian works on every single book that comes in. It's dense because every part of the model is active all the time. Models like GPT-3 are built this way. Some of these have over 500 billion parameters. Think of parameters as individual neurons or connections in a brain. And the other approach is mixture of experts. This is a smarter library. Instead of everyone working on everything, you have specialists. If a book about math comes in, only the math librarians wake up. This allows the model to be massive, like the 1.7 trillion parameter switch transformer, without needing a supernova's worth of electricity to run, because only a small part of the brain fires at one time. So bigger is better, but it's incredibly expensive. The paper notes that we are running out of two things. Number 1 is the money or electricity, or we can sum it up as compute. And number 2 is the high quality data. If we talk about the scaling laws, this is the heart of the research paper. For a long time, researchers followed the Kaplan scaling laws. Kaplan argued that if you have more money to spend on AI, you should spend most of it on making the model bigger, and only a little bit on more data. The authors of this paper realized Kaplan was a bit off. They found that if you double your budget, you should double the model size and double the amount of data equally. The paper explains that the earlier researchers did not tune their learning rate correctly. Learning rate means how fast the AI learns. They used a fixed schedule. It's like a student who plans to study for 10 hours, but the teacher only gives them 2 hours of material. The student ends up overfitting or not reaching their full potential. This paper proved that most AI models were actually overtrained on brains that were too big for the amount of data they were eating. To get a better AI, we don't just need a bigger brain, we need to feed it a lot more data. Building an AI isn't just about size and data, it's about the settings. The paper mentions several technical dials researchers have to turn. Number one is the learning rate, how much the model changes its mind when it makes a mistake. Number two is the batch size, how many flashcards the AI looks at before it updates its knowledge. Number three is width to depth ratio. Should the AI be wide, means lots of neurons in one layer, or deep, which means many layers of neurons? The researchers admit they chose certain designs not because they were perfect, but because they ran faster on their specific computer chips. In the real world, time is money. The paper touches on how we might get around these massive costs. One orthogonal approach is retrieval mechanisms. Instead of trying to memorize the entire internet into its own brain, the AI is given a search engine. When you ask a question, the AI quickly looks up relevant documents and then answers. This is huge because it effectively makes the model seem 10 times smarter without actually making the brain 10 times bigger. It's like a student who is allowed to use an open book policy during an exam. Let's talk about the budget dilemma. Imagine you are given $1 million. You want to build the smartest AI possible. You have two things to spend your money on. Number one is the model size, buying more brain cells. Number two, training data, buying more books or tokens for the brain to read. If you spend all your money on a giant brain but only buy it one book, it won't be very smart. If you buy a tiny brain and 1 billion books, it won't have the capacity to remember them all. So the researchers asks, what is the perfect Goldilocks balance between brain size and books to get the lowest possible error? So they took 3 approaches. Number one is the trial and error strategy. The researchers took several fixed brain sizes from tiny 70 million to large 10 billion and trained them for different lengths of time. Imagine I have 10 students. Student A has a small notebook. Student J has a massive library. I give them different amounts of study time. Then I look at the results and ask, for a student to get a score of 90%, who did it with the least amount of electricity or effort? They found a mathematical power law. They realized that as you get more money or compute, you should not just make the brain bigger. You should make the brain bigger and give it more books at the exact same rate. If you increase your budget by 100x, you should make the model 10x bigger and give it 10x more data. Now let's talk about approach 2. Let's call it ISO-flop profiles. ISO means same. Here they fixed the budget first. They said, I have exactly 10 units of energy. Let me try 50 different combinations of model size and data that all cost exactly 10 units. Imagine you have exactly 1 hour to prepare for a test. You could spend 50 minutes setting up your desk or model size and 10 minutes reading. You could spend 10 minutes setting up and 50 minutes reading, or you could spend 30 minutes on each. When they plotted the results, they saw a U-shaped curve. If the model was too small, the loss was high. If the model was too big, the loss was also high. The bottom of that U is the sweet spot. Again, the sweet spot showed that for every budget level, the best models were much smaller than people previously thought, but they had read much more data. And now let's talk about approach 3, the master formula. They created a mathematical equation to predict the loss based on parameters and tokens. So this formula breaks ignorance into 3 parts. Number 1 is the E. Let's call it the mystery. This is the natural complexity of language. No matter how smart the AI is, some things are just unpredictable. Number 2, A over N, or the brain power. This represents the error caused by the brain being too small. And number 3, B over D, or the lack of study. This represents the error caused by not reading enough books. By fitting all their data into this formula, they could calculate the efficient frontier, a perfect line on a graph that tells you exactly how to build a model for any budget. Now, what was the mic drop moment? The most famous AI at the time this was written was GPT-3. Based on this research, the authors realized that GPT-3 was overtrained in size but undertrained in data. To be compute optimal, a 175 billion model should have been trained on 300 billion tokens. Should not have been trained on 300 billion tokens, but it should have been trained on 3.7 trillion tokens. So the key takeaways were that most AI models are oversized. We build giant models that are actually starving because they have not seen enough data. The researchers built a model called Chinchilla using these rules. It was 4 times smaller than the famous Gopher model, but used 4x more data. The result? Chinchilla beat Gopher and GPT-3 on almost every test, even though it was smaller. So, how Chinchilla was built? To understand the anatomy of Chinchilla, let's look at the changes the researchers made to its curriculum. In terms of the optimizer, they switched from a tool called Adam to Adam W. If Adam is a student highlighting every single sentence in a book, Adam W is a student who only highlights the most important parts. It prevents the model from getting distracted by useless details, leading to better performance in the long run. In terms of the tokenizer, they used a modified sentence piece tokenizer without NFKC normalization. In simple terms, they stopped the model from oversimplifying characters. This is why Chinchilla is much better at math and chemistry. It can see the difference between complex symbols and formulas more clearly than Gopher could. Because Chinchilla has 70 billion parameters instead of 280 billion, it fits into smaller backpacks. It answers questions faster. It's cheaper to use in the real world. Now let's talk about the performance results. The paper puts Chinchilla through a grueling battery of tests. Let's look at the highlights. First, let's talk about the MMLU, the academic exam. MMLU is like a massive SAT exam covering 57 subjects like law, ethics, and astronomy. So, comparison between Gopher and Chinchilla gives us an accuracy of 60% for Gopher on the MMLU, and for Chinchilla we get an accuracy of 67.6%. Chinchilla did not just beat Gopher, it beat the expert human forecast for what we thought AI would be able to do by 2023. It even scored over 90% in subjects like international law and sociology, a first for any AI at the time. On a test called Lambda, which tests if a model can predict the last word of a sentence, Chinchilla beat models much larger than itself, like the massive MT-NLG 530 billion parameters. It showed that having more experience/data helps it understand the context of a story better than just having a big brain. A good teacher does not just talk about the A+ scores. We have to talk about behavior. The researchers used the Vino gender test. This checks if the model assumes a doctor is always a man or a nurse is always a woman. Chinchilla is smarter at recognizing that anyone can be any profession compared to Gopher. It improved much more at recognizing female and neutral pronouns than male ones. This shows that even though the model is smarter, the biases in the books it read are still there. It's an even-handed student, but it still has some old-fashioned prejudices. Does a smarter model becomes a meaner model? Well, no. The researchers found that toxicity stayed about the same, whether a model is small or huge. Its rudeness level depends more on the data it was fed than how many parameters it has. So, breaking the big misconception, bigger is always better. For a long time, the AI world was in a space race. Everyone thought the secret to a smarter AI was simply adding more parameters. GPT-3 had 175 billion parameters, and MT-NLG had 530 billion parameters. However, the researchers noticed something weird. Even though these models were getting massive, they were all being fed roughly the same amount of food/data, about 300 billion tokens. Imagine you are training two students for a marathon. Student A has a normal-sized body, and student B is a giant. If you only give both of them 1 cup of water and 1 energy bar, the giant isn't going to perform better just because he's bigger. In fact, he might perform worse because he requires more energy just to move his own weight. The paper argues that we have been building giants but starving them of data. We were wasting our compute budget. The researchers ran over 400 experiments to find the sweet spot. They wanted to know, if I have a fixed amount of money to spend on electricity/GPUs, how should I split it between model size and training time? They found a specific mathematical relationship. They realized that for every time you double the size of the model, you should also double the amount of data you give it. To prove this, they looked at a model called Gopher, around 280 billion parameters. Let's make it huge and feed it a standard amount of data. On the other side, let's make a model that is 4x smaller, in this case Chinchilla, which is 70 billion parameters, but feed it way more data, 1.4 trillion tokens. The result? The smaller, well-fed Chinchilla outperformed the starving giant Gopher on almost every test. It was faster, cheaper to use, and smarter. The paper mentions something called a power law relationship. In simple terms, this is a mathematical rule that helps us predict the future. It tells us if you give me X amount of computer power, I can tell you exactly how big your model should be and how many books it needs to read to be perfect. However, the authors are honest about their limitations. They notice that at extremely high levels of power, the math starts to curve a bit. This suggests that even their 70 billion model might still be too big and could have been even smaller and more efficient. Most models only read their dataset once, or one epoch. The researchers aren't sure Yet, what happens if a model reads the same high quality book 3 or 4 times? Now, mind it, this is based on the research paper, not based on current times. This is the warning label of the paper. If the Chinchilla scaling laws tell us we need trillions of words to make AI better, where do we get them? You can't just feed an AI garbage data. If the data is low quality, the AI becomes low quality. To get trillions of words, you have to scrape the entire internet. The internet, as we know, contains bias, racism, and private info. Interestingly, Chinchilla was found to be less toxic than Gopher, but researchers still don't fully understand why. The takeaway from this research is that efficiency is king. We don't need larger brains, we need better trained brains. This paper shifted the entire industry toward collecting better data rather than just buying more GPUs.